Everyone ready? Okay. Hey everybody, welcome to Introduction to Embedded Systems. This is going to be our last workshop for this semester. Yeah, a little sad. But without further ado, before I get to the actual workshop, I'm just going to walk through a couple of announcements for ACM here in a sec. So if you haven't already, follow us on social media. We recommend you follow our Discord because that's typically where events are updated the most frequently. Though we still do update our other social medias, I would just advise you to go to our Discord because that's where we'll typically have the most frequent updates. Moving on, and for those of you who don't know, membership is free so long as you attend 9 meetings throughout the semester. Yeah, 9 meetings. And I mean, yeah, it's free. I don't see why you wouldn't. Though, if you remember, you get some other stuff like, like a T-shirt at the end of the semester. You get entered in giveaways. You also are invited to our spring banquet, which is coming up just this Sunday. But yeah, I recommend you join. And so I guess, and for those of you who aren't members, there's also a link and a QR code there. Feel free to scan it if you will. And finally, for graduating seniors, stoles will be distributed at the banquet, so you can pick those up while you're there. And there should be an RSVP link in the Discord, so if you have not done so already, I recommend you do that at your earliest convenience. And now moving on to upcoming events. So these are the last few events. So if you want your membership points, these are the last few opportunities you can go to get them. So today we have a social at the Roost. We're just going to hang out. A couple of ACM officers will be there. We hope we see some of you guys there too. But it'll be a nice kind of relaxed time and just hanging out. That's all. And we also have our ACM special lessons. So that's on Friday, April 29th at 12 p.m. And that's going to be held in the NP 467 room. And we are looking for a technical officer, a finance officer, and an ACM-W secretary. So if you're interested, please apply. And I assume that QR code is for that. But yeah, if you're interested, I would recommend you apply for next year's positions. And finally, as I've only briefly mentioned, we also have our spring banquet. That's on Sunday, May 1st at 1 p.m. We would like you to come in business casual attire. And the only real condition is that you have to be a 2021 to 2022 ACM member to receive an invite. That's all we ask of you. If you're a member, cool, you're good to go. Just RSVP. And finally, after my monologue, please sign into today's meeting. There's a QR code, or you can just enter the link right there. And I'll give you guys a minute to go ahead and do that. Everyone all good? Okay, I'll go ahead and get started. Don't worry if you have not gotten at the end, or here at this moment. I'll bring it up at the end. And I guess before you sign in, you'll probably see a question regarding an interest in something. I will talk about that towards the end. Without further ado, let's get started. So firstly, what are embedded systems? So they're basically just computer systems that interact with the real world. And these are typically utilized with microcontrollers or microprocessors. And these microprocessors aren't full-fledged computers. So they're computers, but they're not computers. They're computers in the unconventional way that they are integrated with some other device, but you don't directly use them like you would with your modern computer, so like your laptop or your desktop. An embedded system doesn't contain this. It contains a microcontroller. So the best way to describe it is a computer, but it's not actually a computer, if that makes sense. It sounds like an oxymoron, but that's kind of the easiest way to describe it. But the question is, why embedded systems? Embedded systems are practically everywhere. Robots, Tesla has tons of embedded systems in them. They have a hierarchy, but even simple things like a laundry machine probably has an embedded system. Maybe you see like a little LED screen telling you the amount of minutes, or telling you what setting you've put. It probably uses an embedded system to do all of that. So that's why they're super important. It's because they're used in so many modern and conventional things. That's why it's so important to have some sort of knowledge about what embedded systems are. So in our workshop, we're going to actually use an Arduino. And although it's a bit more of a hobbyist servo, I think it's a great... thank you, Nico. I'll talk about that later then. So yeah, we're going to be using an Arduino board. Even though it's a hobbyist board, I think it's incredibly simple to get started with. There are tons of microcontroller options, but we can talk about those towards the end. But the question is, so answering the question, how do we actually interact with the outside embedded systems? So we typically use peripherals, so like lights, or other electronic components, and we interact with them on our board. And this is done through general purpose input or output pins. So essentially what these are pins on your board that take in some sort of analog or digital signal, and you provide it to these pins, either as an input or output. Thus the name general purpose input or output. And this is like the main way we interact with our components. For those of you who are aware, the difference between an analog and a digital signal is that an analog signal is a bit more continuous, while a digital signal is discrete. A digital signal has a 1 or a 0. It's either on or off. Unlike an analog signal, where we have many values that are 0. Like you could have range of from 0 to 1. That's the main difference. And so, like I said, we're using the Arduino Uno, and I understand that not everyone online has the hardware, but I can still sort of teach you what's going on here. And so for those of you who do have the hardware and can follow along, first just go to this link, which was posted in the stream chat, which I think can be posted again, if that's fine. So we have this link, and basically when you go to it, you'll be redirected to a page where you see the installation for the Arduino IDE, depending on your operating system. So I can actually show that really quick here. So let's go to that link. So if we go here, if you just download whatever version, in my case, I would just do Windows 7 or newer. Just click that and then just follow the installation process, which if we go, yeah, this is fine. So if we go through that installation process, excuse me for a sec. So if you go through that installation process, you can just leave the defaults as is and just continue onwards. Should be okay. And so just to give you some context, Arduino programs are kind of programmed in a C-like language where you have one function for setup, which initializes all of your pins, your ports, and whatever you need to do before your main. So we're actually running the entire program over and over. Your setup just handles all of the stuff you need to initialize before you do your main loop. And your main loop is actually what's constantly running on your microcontroller. And this is a C-like language, so I'm sure some of you have programmed in C before, at least a little bit. And even if you haven't, maybe something like Python, you'll probably be a little familiar with what's going on here. So without further ado, let's actually get to the hands-on stuff. So we're going to talk about a couple of electronic components. And the first one up is a light-emitting diode. And this is like, it's basically just a semiconductor that emits light. And you have the anode and the cathode. And the anode is basically the positive side, so where you actually feed in voltage to it. And cathode is the ground, so where you're feeding in like either 0 or negative voltage. And so the anode and the cathode are indicated by where the anode is the long leg and the cathode is the shorter leg or lead. And so the reason I wanted to use an LED for this scenario is because it's kind of a very easy, simple way to get started with our digital input-output pins. So what I'm going to do right now is I'm going to go ahead and start wiring the actual Arduino. So I use this wiring diagram here. Feel free to follow along, but what I will do is I will start wiring it up. And if you will pull up the hand cam on StreamYard, please. Perfect. Okay. So basically, a breadboard works kind of in the way, I don't know if you can see that, but the breadboard kind of works in a way different than the rest of the wiring diagrams, but what I'm going to do is I'm going to take this positive pin and I'm going to put it on that little slot that says 8. So on your boards, you probably have something that says digital PWM and it has like the little 8 there. That's where we're going to put our pin. And so I'm going to actually walk through this quickly, but what I will do is I'll walk around and I'll, for the in-person people, and I'll try to explain things as they go. So now what we can do is, although we typically have a resistor in our diagram, what we can do is, for now, try using the resistor and see what happens. And I'll kind of show you what goes on. So just remembering longer lead. So that's the longer lead. So I'm going to put the resistor on the same row as the long lead of the LED. And I'm going to put the resistor on some other row of the breadboard. Doesn't matter, as long as you know that row. And then you take that row and you take another column that's empty and you hook it up to the positive rail. So it's a little hard to see, but basically so that's the longer lead of the LED. I took a resistor in series and then I hooked that series to, using a wire, to the power rail, which for now we have as our digital input. And so the next thing what I will do is, what I'm going to do for now actually is just directly connect this shorter lead to the ground pin on our Arduino, and you'll see it labeled as G and D. So what I will do now is I will pull up the Arduino code to actually power this LED on and off. And then what I will do is I'll kind of show you guys what's going on here. So if we pull up our Arduino code, which stream, please. I don't know if stream can see that. The stream can see that or not. I'm gonna have to zoom in a little for the in-person people, but so what's going on here? So after you've wired it correctly, or actually, yeah, so I'm gonna actually change this to 8. But basically, what's going on here is if that's easy to see, what I'm doing here is I'm basically saying, okay, the LED pin is an 8, and I'm going to label this as an output. I'm going to make that 8th pin an output, that digital 8 pin an output, because what you're doing is you're outputting a 1 or signal to the LED. That's how you're actually lighting it. And so then, after I've done all my setup with making the pin an output, what I do is I write a 1, so an on, to the LED pin. I delay it by 500 milliseconds, so half a second, and then I write it as a low, or excuse me, I inverted that. So this is actually 1, this is a 0, and then I'm going to delay it by about 200 milliseconds. So in the Arduino IDE, what we can do is we can verify, and what this does is it basically verifies that your code is all working, which it might take a little, but I'll walk around a bit and show you guys what's going on. So wiring it a little, compiling it, and now what I'm going to do is I'm going to plug in my Arduino. So depending on your port, you'll plug it in. It's this kind of block here, and then that usually has a USB on the end of it, and you'll plug that into your computer. And so once you've plugged in that Arduino into your computer, what you can do is go under Tools here in Arduino, and then select Port, and then make sure that's the, and then you should see something like COM whatever number, and that should be labeled as an Arduino Uno. So select that. Then what you want to do is upload, and your code should work now. So now what I want to show everyone is that this LED, it kind of looks a little empty it doesn't look like it's blinking from far away. I'm going to show the stream here. So the LED doesn't actually, it looks like it's blinking a little, but it's really dim. So the reason for that is actually because of our resistor. And so these GPIO pins actually run at 3.3 volts. And this resistor is essentially trumping that current. So the more current or voltage we feed in, the brighter the LED should be. However, the problem is that you don't want to feed so much voltage that it actually dies, or it's too much and it actually just blows out. And so what I actually want to show you guys is a data sheet. And so the reason I want to pull up this data sheet is this is not our same LED, but this is an example. Bless you. And so the reason I want to pull up this data sheet is because reading data sheets is such a crucial skill for embedded systems. It tells you specifications about a part, what can it do, how does it operate. And so typically, LEDs will operate at a forward current. And so that forward current is actually what goes through and lights up the LED. And the forward current is a max usually of 20 milliamps. I think in this, yeah. So in this case, they did a test condition of 20 milliamps. In this case, they have a peak forward current of 1 amp, but 20 milliamps is usually sufficient. But the reason we want a resistor is because we want to find the right resistor that will make it so that enough current flows through that it lights up bright enough. And so picking up valuable pieces of information about how an LED works through a datasheet and other components, other embedded systems through a datasheet is so important. And so basically the reason why our LED is because we're putting too much resistance into it. If we switch back to the hand cam, right? So if we switch back to the hand cam, and let's say I take this pin and I actually put it on the LED itself, you'll actually notice that it starts to blink way brighter than it should. And obviously I'll take off this resistor, but you'll notice it blink way brighter than it should. And this is because our Arduino is running at 3.3 volts, and the current that goes through, or the current and the voltage that actually goes through that is not enough to actually blow out the LED. And that's why and because there's no resistance that stops the current, that's why it's so bright. So now I've kind of shown you how I do it and how it's programmed. What I'm going to do is I'm going to come around a couple of tables, and I'm going to help you guys if you need it. Does that sound good?
Yes.
Okay. So stream, I will be right back. Feel free to ask questions in the chat, and I'll get back to you guys. Okay. So, you guys doing good? I know you don't. Okay. Yeah. Okay. Hey everybody, welcome back. So now that we assume we've given you enough time to wire it up for the online people, let's actually move on to another component. So I've kind of shown you basic. So actually, let me swap to the code here for a sec. So basically, just reviewing it over, we're basically saying, okay, make your LED pin at that eighth D8, so the digital 8 pin, and then set it as an output, and then make the LED blink by turning it off for 500 milliseconds, then on, and delay by 200, and then this just repeats. So in the wiring diagram, it's a little difficult to see, but you can see that where the resistor is, that positive end goes to D8, wherever we're actually having our LED. So I don't want to spend too much time on that, but I want to move on to our next electronic component. And this one's particularly useful for a lot of applications like robots. If you need to measure if there's a wall in front of you, we have something called an ultrasonic sensor. And so basically what these are is that they're devices which send in a sound wave, and then once that sound wave is reflected or bounced off an object, they have a receiver which actually takes in that sound wave, and then that is actually, and so basically you find out the time it takes to bounce out a sound wave and take it back, and you use that to calculate your distance through a very easy conversion. So you can convert like microseconds to like centimeters or inches. And so, yeah, so these are really useful for just calculating distance. And what I'll do here is I'm going to show you how to wire the ultrasonic sensor to your Arduino. So this is a little different than how we did our LED, but the concepts are mostly the same, that you take in some pins and then you put them to whatever digital inputs outputs you need, and so on. So just to show you what's going on with the hand cam here for a sec. Oh, it's a bit hard. Oops, I guess I didn't see that. Okay, well, that's fine. So so just to show you what's going on, so hand cam. So I'll just disconnect everything here for a sec. Try this off. Take the LED. And so what I'll do now is so what I'll do first is I'll make my voltage and my ground parts, I'll put them to the power rails. So wherever it says 5V on your Arduino board, you hook that to the positive rail. And then wherever it says ground on your Arduino, you take that and you hook it to your negative rail. So it's a little hard to see, but I've hooked it up. So I've hooked up a ground to the blue rail and a power to the positive rail. And also just keep in mind too that these two rails, the left and the right rails, are separate. So even though you deliver power on like this left hand, I guess my left hand rail, this right one isn't actually affected. So you will have to make a connection there, but just note that. So once I wire these up, what I'm going to take is I'm going to take my ultrasonic sensor here, and I'm going to put that just here. And so these are basically 4 separate rows, so I can easily kind of show you. That may be hard to see. I put in like 4 separate. So I oriented it so each pin is in each different row. Well, this is going to be important for hooking things up. So first things first is you take whatever is at, so the pin VCC, and you hook that to the positive power rail, because that's actually where we have our 5 volts. and we want to supply 5 volts to this ultrasonic sensor, and then take in another wire, and in the same row as ground, hook that to the blue power rail, because that's your ground. And so it's a little hard to see, but I've kind of hooked up that green one to ground, and that white one to the red rail or power. So now that we have done that, just double checking my wiring here. Now that we have done that, right, we now have 2 pins left, trigger and echo. So remember that I believe, let me double check. So remember that trigger is pin 12 and echo is pin, well, trigger is 11 and echo is 12. So following that, so finding the row of the breadboard that has that trigger pin, you hook that trigger, and what you do is on your Arduino, you find wherever pin 11 is, or D11, so that's our digital pin 11, and then applying a similar process, which, that wire might be too short. Let me fix that. So 11, so pin 11, hook that up to trigger, and then 12, hook that up to echo. So 12. So it's a little hard to see, maybe, but just know that, so yeah, we basically hooked up this D11 here, so it's a red wire, to wherever on the breadboard it says trigger, and then echo to where on the ultrasonic sensor, or the row that has echo, to the 12th pin. And so this is good for distance. This is good for our wiring schematic. So now to actually demo some of the code here, so let me show you guys some of the code. So basically what I've done here is I've used a couple. So rather than just typing out 11, 12, I think it's better as a convention to clarify which pins are which. So echo is pin 12 and trigger is pin 11. And so in our setup here, what we do is we begin a serial connection, and the reason we want this is because we can actually print our distance just using Arduino. That's why we want it. And so now, like the LEDs, we have to configure our trigger and echo pins to what they need. So our trigger is going to be an output because you want to, you output a sound wave, and our echo is going to be an input because you're taking in a sound wave. So that GPIO pin is taking in some sort of input. So following along, we don't actually need this because we already set up our pins. But basically, first thing we do is we write to our trigger pin, and we write low. We delay it by a couple microseconds, so 2, and then we delay, and then we write high to the trigger pin. So this is actually what's emitting the sound wave, and then we wait for 10 microseconds, and then what we do is we get the duration, so how long it takes for that echo pin. So we do that by taking this pulse in. So we basically see how long did it take for that echo pin to receive a sound wave bouncing back. And then what we do is we just use this formula to calculate the centimeters. So we essentially convert our microseconds to centimeters. And we do this through just dividing by 58.2. And so now what we do is in our console window, or where we're actually going to monitor our distance, we printed distance, then our actual distance in centimeters, and we print a line. And then we delay that by a tenth of a millisecond, or a tenth of a second, sorry. So now, assuming I have everything wired correctly, and then plugging in our Arduino in, let's go ahead. So here you go. So I've connected this back to my USB. We're going to go ahead and click that verify button right there, or well, just upload, because I think this code should work perfectly fine. And so now it actually does work. So what we can actually do is monitor our distance by pressing Control-Shift-M, or what you can do is you can go to Tools, up Tools, and go to Serial Monitor, and that should work. But for here, what I'll do is I'll show you what's going on. So this is a distance in centimeters. So the thing is it doesn't actually see anything. So basically, if I point it out that way, it doesn't really see anything, which is why that distance in centimeters is so high. However, if I put my hand closer to it, you'll see that the distance actually drops significantly. And then if I go closer and closer and closer, your distance becomes more and more closer to 0. So now that, because that sound wave is traveling a shorter distance, that's actually why you get a smaller distance in centimeters. Does that make sense to everybody? Okay. So I'm going to come around and try to help you guys for a sec here.
What happens if you scream at it, Alex?
What?
What happens if you scream at it?
Can you scream at it and it changes the frequency?
So before I go, someone asked. I'm doing that. So before I go, someone asked if I scream into the sound wave, will it change anything? I do not know the answer to that question. We're gonna try. Nah, I'm gonna spare the online audience from that. You can. Nah. Okay, welcome back, everybody. Apologies for the delay. I know I know I've been going for quite a while, but I'm going to go back to the PowerPoint and try to speed through some of the other stuff I had planned in mind. So now that I've shown you how to measure distance, how to wire things up for your ultrasonic sensor, now let's talk about another nice tool that we can use called LCD screens. So I'm sure most of you are familiar with what an LCD screen is, but they're relatively simple. They can display really basic information like text, and they come in a variety of sizes. So like 2 by 16 meaning 2 rows and 16 columns, 2 by 40, 2 rows, 40 columns, and so on and so forth. But they're really nice for displaying basic information. And what we're going to do is we're going to wire up one up to our previous circuit, and we're going to build off of it. So going back to our hand cam here, and I'm messing around with our circuit. So basically, these LCD screens on the back, they have and they basically have these little attachments here, and this is for something called I2C, and that's actually how this screen communicates to our board. You don't need to understand the deep details of I2C. Just understand that it's used for communicate with the it's used for the LCD to communicate with the Arduino. And so for now, I'll show you how to wire it. So going off of our previous setup, basically we look at our back pins, and so kind of following most of the same convention as we have before. Basically take our wires and make sure you have a male to female wire. And so I'm just gonna quickly hook these up all there. So kind of quickly hook these up, just using a male to female. Take the female side and hook it up there. And then take whatever pin is on ground. So in my case, it's the white pin. So this white pin that's on ground. So whatever's on ground, hook that up to the blue power rail, because that's what we said is ground. And then wherever our voltage is, so in my case, it's the gray wire, hook that up to the positive rail. And then finally, for SDA, so for SDA, which is the purple wire in my case, we want to hook that up to wherever SDA is on this board. Typically, Arduinos will tell you what SDA is. In my case, my board does tell me what it is, so I'm going to hook up this wire, so SDA to SDA, and apply the same thing to SCL, where we hook it up to SCL. And now our LCD screen is actually on. Some LCD screens, the backlight may be really kind of bad. But this is how it should kind of look like, where the backlight is on, but nothing's actually on yet. So if we swap back to our code here, so give me 1 second, guys. If we go back to our code here, swapping back. So what I want you guys to do is I want you guys to go and install a separate library. So to do that, go to Tools, Sketch, I believe. Yeah, Sketch, and then go to Include Library, and then click Manage Libraries. And so what I want you guys to do is install a library really quick here that will actually help us communicate with this I2C. So, So under Sketch, Manage Library, or under Sketch Libraries, you click, or Manage Libraries, you click Add a new library, or base Manage Libraries, whatever that setting is, which, let's go back actually. Can I do that? No, I can't. Okay, well, so once you've selected the ability to manage your libraries, what you want to do is basically look up Liquid Crystal, and then I2C. And so now, what we're going to do is we're going to use this library, which is this one by Marco Schwartz, and it's just called Liquid Crystal I2C. And this install button should be highlighted for you, so just click it and install it. And then once you've installed it, go back here. And what we can do is, I'm just actually going to go to some line of my code, click on Tools, Sketch, Include Library. And then you should have a new contributed libraries, Liquid Crystal I2C, and that will include it for you. You don't actually have to type it out. I've already done the heavy lifting, and I've included it already. But once you've installed that library, then we can actually work with these LCD screens that we have here. First one here basically sets up our LCD screen. And so I2C has like slaves and masters, and that's how like the communication protocol works, where like one like commands the other. And in order to do that, it needs to know where the slave is at. And because our slave is the LCD screen, I believe, we set our address to 0x27, which on this particular board is, I believe, just 0x27. Then we set up our width and our height, which is a 16:2 LCD. And then we set up all our stuff. So we initiate this LCD, turn on the backlight, and then we set the cursor to 0, 0. So that's the very top leftmost position. And then we print out the distance. And I've also done serial stuff here, so in case we want to actually also see it on the serial monitor, we can do that too. And then same setup as the ultrasonic sensor. The only difference here is that now I'm setting the LCD cursor to the left position here. And then what I'm doing is I'm just using lcd.print to actually print out the centimeters in our length. And I'm actually going to change this delay to half a millisecond, or half a second, so we can actually see what's going on. So now if I compile that, if I upload it to our Arduino, it'll take a little bit. What's up? Sure. Yeah. So going back to our code, yeah. So make sure that you initiate it. Make sure you initiate it. Set the backlight. Set the cursor. Then print it. And that's what you're doing for the LCD stuff. And make sure, obviously, first before all that, you initialize your LCD as a 16:2 at the slave address 0x27, which my backlight is not good. Let me fix it for the stream if you can see it. Perfect. So now, So I just adjusted the backlight. I used a little tool here to actually, if you'll switch the hand cam. So I used a tool here to adjust the backlight of the LCD, because these actually have a potentiometer in the back that adjusts the brightness. And in order to more visibly see what's going on, I've done that. So I've hooked up the LCD, and I've shown you the code. So if we actually look at the LCD here, we can notice that an actual distance is being printed. And so if you guys can see that at the stream chat, we can see a distance. So yeah, so now we see the distance is large, kind of like what we saw before, but if we go closer and closer, it's a little scrambled up, but we can actually see that the distance, so you can actually see the distance is decreasing slower and smaller and smaller and smaller. Yeah, and obviously it's too close, so it doesn't know, but yeah, we can actually see on our LCD, just like our serial monitor, the distance actually changes. So this might be better as an integer, but double is fine. If you're familiar with programming, I've just used a double to represent our distance in centimeters. But we basically just printed out all of it in this LCD screen. So now what I'm going to do is I'm going to come around to a couple of tables, and I'm going to try to help out. So I'll be right back in 1 second.
Yeah, I think this one is medium difficult.
Okay.
Because everybody wants like
Hey everybody, welcome back. Okay, apologies for the wait. For the stream viewers, let me just show you one more time what's going on with the distance, just so you see what's up. So we basically just displayed our ultrasonic distance on this LCD, and we have this ultrasonic sensor. And if I put my hand closer to it, you'll kind of see the distance change. And you will notice that there's a little glitching with these like decimal points. And that's because some of these are just overriding the previous ones. And that's why you see that kind of overwritten numbers. But yeah, basically, I think I'll wrap it up there. But what I wanted to show you guys, PowerPoint. So going back to our PowerPoint, we don't have time for servos, but just know that they're basically a way to rotate objects, and they go from 0 to 180 degrees. And you typically use something called pulse width modulation to rotate these. And essentially, what it does is pulse width modulation takes the digital like voltage, and it kind of converts to like an analog sort of reading. And so the reason this is so useful is just because we can actually vary the angle in which our servo turns. And that's why we want to use PWM, because it gives us like a way to vary the angle in which it turns rather than feeding in a constant like voltage. I won't go deep at all, and we don't really have time for servos, but I just want you to be aware that they are there. I do have a wiring diagram for servos, so if you want to follow along and you do have time, feel free to take a look. It's mostly the same as our previous steps, except what I've done is I've hooked up that extra green wire. The black and the red wires are just going to ground and power respectively, and then the green wire just goes to whatever next digital input you have available. It's a bit hard to see, but that one I believe is 13 for our next servo. And so I'll probably upload this code to a GitHub later, so if you guys are interested, you can feel free to scope out the examples. But yeah, wrapping up our presentation. So where do we go from here? I know Arduinos are a really simple hobbyist board, but there are tons of options out there. You have Raspberry Pis, which can run Linux. You can run C code on them. Like they're fantastic options which used to be relatively cheap. They're kind of expensive now. But there's a ton of other microcontrollers that might suit your needs, like the STM32s, the PIC microcontrollers, or the microcontrollers from NXP. You have a ton of options, and they have better use in some scenarios. So you might need less power consumption, or many modes of sleep, or you may need something like that's very specific to your design. So that's why you want to use these other micros. But then there's other. Yeah, I agree, Pizza Sloth. They're pretty simple. I recommend it. But other options or other topics when concerning microcontrollers, consider looking into analog and digital. Basically, this is so important because you can take varying signals. Hey, camera. We can take varying signals that are like not discrete, and we can actually convert them to a digital reading, and that's more easily readable by our microcontroller. So, for example, like if you want to take in if you're using a temperature sensor and you want to take in that temperature and read it on your microcontroller, there are little like temperature sensors out there that will kind of give you an analog signal, and then it's sort of up to you to make that a digital signal. So that's why we want analog to digital converters. It's kind of like how phones will take in of your voice and they will make it into a digital signal. They use analog and digital converters for their microphones. That's why they're so important. Like I discussed, pulse width modulation turns a digital reading to an analog reading. And then you have other communication protocols. So like I discussed, I2C is a way in which our LCD communicates with our board. And there are many other communication protocols like I2C, SPI, and they have varying uses. They have certain scenarios where we want to use it. It's really case-by-case basis. But I recommend you learn them. They might be very useful to you. And then finally, what I recommend is just reading data sheets. So I only went to a brief segue in this stream, but I think reading data sheets is an incredibly valuable skill because you want to understand how does a component operate, what are the limits, can I push this component to do X, Y, or Z, like our LED, right? the data sheet answered our question, like how much current can we feed? How much forward current can we feed before it blows out or it goes on, it's in safe conditions. So reading data sheets and understanding specifications is super valuable. And finally, one last announcement before I wrap up. I am considering on doing an embedded systems study group. I will post an announcement on Discord later. But if people want to follow along, that is fantastic. And I do have a tentative plan with it. Hopefully, I can teach you guys more about microcontrollers, and we can go into more specifics, and hopefully get a project out of it. So that's my plan for hopefully late into the summer or in the fall. But yeah, feel free to ask me questions if you have anything regarding that. But finally, feel free to sign in if you have not. And there's also a QR code if you want feedback about the embedded systems. I've also provided a link. But if you have any opinions, please feel free to give them to me. I want your feedback. I want your opinions. And that just doesn't go for this study group. This goes for all intro to techs. I want you guys to be honest with me. I want good constructive feedback. And I want to know what people think of what I've done so far. And even though it's been a pleasure to do these intro to techs, sadly it has to come to an end for this year. But yeah, I'm just I'm looking for the feedback, and thank you guys. And that'll be it.
Your type form isn't open.
It's not open. Zach.
I have no idea.
You didn't make it.
Guess we're fixing issues with the type form. Cool.
Elijah's gonna fix it.
Okay.
What would you name the type form?
Huh?
What'd you name the type form? EBFU.
You see what we put on our
I don't actually know the name.
Talk to your fans.
Hello, fans. Welcome back. I think the type form should be promptly fixed, and it should be good to go, right, Elijah? Okay. We'll give it a couple minutes, and we should have that type form good to go. But if you haven't signed in already, please feel free to do so. But I think that should mostly be it, right? That's okay.
Give it a second, and I'll let you know.
Okay.
Tell me when they click the link. Okay. Tell them your favorite Linux.
Huh?
Tell them your favorite Linux distro.
Debian.
Tell them.
Oh. Hey, everybody. What's your favorite Linux distro? Mine's Debian. Debian's great.
You said my name's Deviant.
My name's Debian? My name's Debian. Hey, guys.
The link is up and running.
Yeah. Okay. Whoever's still watching, link is up and running. So if you have not signed in yet, go ahead and do so. But that should be it. Thank you guys for attending the streams. Really appreciate your time, and I hope you guys got something out of it. Yeah. Thank you. Thank you, guys. Yeah. 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 Yeah, sure. I'll see you in a sec. It's okay, guys. If you screw up, I'll figure it out.
It works.
It works? Okay.
A little too left, I think.